So we already learned how to do add, subtract, multiply to complex numbers, and then we're going to study how to divide to complex numbers. But before we can learn how to divide to complex numbers, we have to introduce a very important concept. What is the conjugate of a complex number? Okay, so we say if complex number z equals a plus bi. Okay, this is a complex number, a plus bi. And then its conjugates, conjugates defines or denoted by z bar. Okay, z bar, that's the notation for conjugates of the complex number z. Just put a top, very short horizontal bar on the top of the complex number. So z bar, or conjugates of z, can also write as a plus bi bar, which is equals a minus bi. Okay, so what is a conjugate? Conjugates, that means a complex number real part remain the same. Okay, but the imaginary part is opposite sign. Opposite sign. So if originally is positive, and then the opposite sign will be negative. Okay, for example, if I say 7 plus 5i, and then the conjugates, okay, if c equals 7 plus 5i, and then the conjugates of c will be 7 minus 5i, right? If c equals 3 minus 4i, and then the z bar, the conjugates will be 3 plus 4i, right? If z equals negative 1 plus I, what is z bar? Z bar will be negative 1 minus I. Okay, so be careful. The real part must remain the same. Only imaginary part, the sign, opposite. Okay, so the common mistake students will make will be, let's say z equals negative 5 plus I, and then conjugates of z is a 5 minus I. This is wrong. Can you tell where it's wrong? Its imaginary part also flip the sign. Okay, that is not correct. Okay, this is wrong. All right. Now let's try. Multiply a complex number by its conjugates. Okay, find the product of complex number z equals 3 plus 4i and its conjugates. So first we need to find the conjugates. Okay, what is the conjugates of 3 plus 4i? So that's 3 plus 4i, find the conjugates, which is what? 3 minus 4i. Is that right? All right, now let's do z times z bar. Complex number multiplied by its conjugates. That's 3 plus 4i multiplied by 3 minus 4i, right? So we already learned how to multiply to complex numbers. We use a FOIL, right? FOIL rule. All right, let's do it. First term, 3 times 3. I just write detail, okay? Second term is plus 3 times negative 4i. Inner term, 4i times 3. Last term, that's 4i times negative 4i. And then we simplify. 3 times 3 is 9. And then second term, 3 times negative 4i, that's negative 12i. 4i times 3 plus 12i. And then the last term, be careful. Okay, last term is what? I put in here, okay? 4 times negative 4, that's negative 16, right? I times I, that's I squared. Remember, I squared equals negative 1, right? That's by definition, that's negative 1. So it's like here we're doing plus negative 16, that's 4 times negative 4, right? Multiplied by I squared, which is negative 1. So negative, that gives us positive. Okay, this term actually positive 16. So 9 plus 16, that's 25. And then you can see right here, outer term, inner term, okay, actually they're cancel out, right? So two conjugates multiply, outer term, inner term, always going to cancel out. So only first term and the last term. And the last term, I squared equals 91. So it's always become a squared plus b squared. Okay, if complex number a plus bi, right, times a minus bi. And it results in always equals a squared plus b squared. So actually we have a theorem. This is just what I did in the previous slides. So here comes the theorem. Two conjugates multiply. Okay, conjugates z if we denote it as a plus bi. So the two conjugates multiply is equals the sum of two squares. Okay, this is the real part square. B, that's the imaginary part square. Okay, always, you just remember this. Okay, this is a theorem already been, proved. So you can apply this theorem directly in the future. You don't have to do the FOIL all the time. Okay, remember two conjugates of complex number multiply. The product is the sum of two squares. Okay, sum of real part square, imaginary part square. So why we need to learn that? Because we need to use that in our division problem. Okay, so how to do the complex number division? The rule is we do not want imaginary part, okay, or imaginary unit. We don't want the I on the denominator. So actually two complex number division is just rewriting. Okay, get rid of the imaginary unit from denominator. So we know this principle. When two conjugates multiply, we get a real number, right? A squared plus b squared. A is a real number, b is a real number. So two real number square, still real number. The sum of the two real number, still real number. That's why we perform two complex number division. Actually, what we do is multiply by numerator and denominator, both by the conjugates of the denominator. So we do 5 plus 12i on both numerator and denominator. So in that way, it's like we multiply by 1, right? We doesn't change anything, but we convert the denominator complex number into a real number. Okay, that's the purpose. All right, let's try. So two conjugates multiply by the theorem is just 5 squared plus 12 squared. Okay, here the sign always positive sign. And then numerator, we have to do the two complex number multiply, right? 1 times 5, that's a 5. 4i times 5, that's 20i. Okay, you can do first, outer, inner, last. I just do the other way. That's plus 12i is the same, right? And then 4i times 12i, that's plus 48i squared, right? Okay, and then remember this is 91, so that's put us to 5 minus 48, that's negative 43, that's the real part, right? Imaginary part, 20 plus 12, that's 32i. Denominator, that's 25 plus 12 squared, that's 144, right? So that will give us negative 43, that's numerator, divided by, okay, let me write one more step so you won't get confused. So numerator, negative 43 plus 32i, denominator is 169, right? But this is not the final answer yet. Okay, why? because we need to writing the quotient of two complex numbers in standard form. Standard form means what? It's a plus bi form. So we have to isolate real part from imaginary part. Okay, so the last step, what we need to do is minus 43 divided by 169, that's the real part. Okay, so this part is the real part. And then plus 32 over 169, and then I right in the middle. This is called a standard form. Okay, so the answer is negative 43 over 169. This is the real part, plus 32 over 169i. So let me check. Yeah, that's the answer, right? It's the same, right? Yeah, that's correct. Okay, let's try the B. Okay, remember what we need to do? We need to multiply the conjugates of the denominator, which is 4 plus 3i, right? But we can't change the problem, so we have to do numerator the same thing. And then simplify. Denominator just 4 squared plus 3 squared. Okay, this sign always positive sign. 2 squared add together. Okay, 4 squared plus 3 squared. And then numerator, okay, FOIL, 8. Okay, this time I do the FOIL. Okay, plus 6i, inner, minus 12i, last, that's minus 9i squared. And then remember I squared equals 91. Okay, so denominator, simplify the 16 plus 9. Numerator, this real part is 8, and then negative 9 times negative 1 plus 9, right? That's real part, plus imaginary part 6 minus 12i. And then further simplify the 17 minus 6i. Denominator is 25. Are we done yet? No. Okay, we have to isolate. This is the real part, and then this is the imaginary part. Okay, so that's 17 over 25 minus 6 out of 25i. This is called a standard form, a plus bi, standard form of complex number. Is that right? 17 out of 25? Right, minus 6 over 25. That's correct. Okay? And then another theorem say the conjugates of a real number is a real number itself. That makes sense, right? Because we say the conjugates of a complex number, real part must remain the same. Imaginary part do the opposite sign. So for example, if a 5 plus 0i, right? If we write as a complex number, that's actually a real number, right? That's actually a 5. So the conjugates, real part need to remain the same, right? And then minus 0i, right? So that's the conjugates. That's why still equals 5. That's why the conjugate of a real number is the real number itself, not the opposite sign. This is wrong, right? So remember that. And we're going to study a few more theorems. The complex number, if we do 2 times conjugates, that go back to original complex number. Think about, does that make sense? For example, let's just use a concrete example illustrating. Right? If z equals 3 plus 5i, and then z bar will be 3 minus 5i, right? Flip the imaginary part sign. And then if we do one more time conjugates, bar and another bar, find the conjugates of z bar, that's go back to 3 plus 5i, right? Flip the sign 2 times, plus, minus, and then go plus again. So that's why it's the same as original complex number. So that's what this theorem talk about. The second theorem saying the conjugate of sum of 2 complex numbers equals the sum of their conjugates. So in other words, the 2 complex number, you add them first and then find the conjugates, will be the same as each complex number find its conjugates and then do the sum. So the order of the conjugates doesn't matter. you can do the sum first and then do conjugates, or you can do conjugates first and then do the sum. Okay, that's what this theorem is talk about. And the last one, the product, okay, the conjugates of the product of two complex number equals the product of their conjugates. Very similar as the summation. The product works the same way. You want to multiply the two complex number first and then find the conjugates. Okay? It's the same as you find individual complex numbers conjugates first and then find the product. The order doesn't matter. You can do either way. Okay? So adding and multiply works the same. You can do adding or multiply first, then do conjugates, or you can do each complex numbers adding or conjugates first. Each complex numbers conjugates first and then do the adding or multiply. Okay, that's what this for.